Hi everyone. My name is Adil Hussain. If you guys remember me, I was one of the people who did the orientation video. Today we're going to be covering computer vision. And the lecture shouldn't be too long. I don't think it'll be all of the 2 hours. I mean, I guess you guys will see. This is a pre-recorded video, but you guys will see. But yeah, I hope you guys learned some stuff, and let's get to it. So, basic like overview of what we're going to be learning. Really it's going to be what is computer vision, how is computer vision like used today, and like what industries it's used in, the most popular like tools and libraries, and we'll talk a little more about that later. Companies, universities that are like exploring, investing, stuff like that in computer vision. And after that, I'll start to get into like, the complicated stuff of how like the computer science behind computer vision works and all of that, convolutional neural networks, recurrent neural networks, stuff like that. And then I'll finish it off just by telling you guys about like a project kind of. Yeah, you guys will see when we get there. So basically, first thing we're going to talk about is what is computer vision, right? And I think the best way to think about this is by just imagining yourself like walking around, driving, sitting in a classroom learning, and all the time you're looking at stuff and your brain is able to instantly understand what you're looking at, right? So for example, going on a drive, right? I see a stop sign. In my mind, it's an instant reaction to, or instant I know instantly that I have to stop at the stop sign, and I know what it means, right? And computer vision is basically when a computer is trying to replicate this process by looking at an image and trying to understand what it is, what's going on in the image, and what's happening, within the context of such an image. And so, like the official definition of computer vision is that it's like a field of AI that enables computers and systems to derive meaningful information from like digital images, videos, and other like inputs. It can see images like the picture of the Labrador on your screen, and it will be able to convert this picture into, or rather, it would see this picture as an array of integer values that represent different color intensities across the image. And it's the ability to analyze such data and make meaningful outputs out of it that is like the foundation upon which like the concept of computer vision is built. So now let's explore like how CV is being used in the world today, right? So I've broken down the uses of computer vision into like I think like a couple meaningful industries. Obviously computer vision is growing in popularity pretty much daily now. It's being used in more and more places. But these are some of the things that I thought were pretty important for you guys to know. So first is the healthcare industry. There's three main ways in which computer vision is used here. X-rays, pretty self-explanatory in that like it allows doctors and ER operators to analyze X-rays efficiently and accurately. And the full automation of this process would mean that patients can get like detailed reports of like fractures and breaks really fast. MRIs and CT scans, it's similar to X-rays, but it's a little more complicated because they're more detailed scans. So like computer vision can help doctors detect tumors, internal bleeding, clogged blood vessels, and like other life-threatening conditions. And the automation of this process has already been implemented, and it's increased the accuracy because obviously machines can detect details that are invisible to the human eye. And like the image on the bottom right, it's an example of a ML-assisted brain and spinal cord annotation. So I think that's pretty cool. And then the third use case is that of cancer detection. So image recognition allows doctors to identify anomalies and changes by comparing cancerous and non-cancerous cells in images, right? And again, automated detection allows for a faster cancer diagnosis using these data from scans such as MRI scans. And in fact, computer vision has already been successfully applied in breast and skin cancer detection. Next, I want to talk a little bit about transportation. This is kind of the biggest industry that people like will know computer vision in because obviously autonomous vehicles, cars like the Tesla are what people think of first when they think of computer vision. So in 2022 and going forward, self-driving cars are very much like a reality, with companies such as Tesla and Google's Waymo on the precipice of like such technology. It's easy to see like what the future holds for autonomous vehicles, right? So computer vision specifically is used to detect and classify objects, whether that be road signs or traffic lights, create 3D maps or like motion estimation, and it plays a key role in making like autonomous vehicles a reality because obviously the cameras and the sensors in the car will be taking in the data around them, and the car has to interpret that and then make decisions. And that's pretty much what like self-driving is. But apart from that, there's a couple of other things it does in the transportation industry as well, like traffic analysis, in which drones and cameras basically analyze traffic patterns, which can like make just more freeway travel and more city travel more efficient. And road conditioning monitoring basically looks at like asphalt and concrete over time. And the algorithms, the machine learning algorithms will collect like image data that's processed to look for cracks and potholes and problems in the roads, and then they can send out crews to do preventive maintenance and stuff like that. And it's really successful in increasing efficiency and decreasing just general risks while driving. Uh, Another one that's another industry that's pretty common is the manufacturing industry. There's a couple of things where computer vision is really helpful in. I think the biggest application here is reading text and barcodes via optical character recognition, which is OCR. You guys might have heard of that. But it's a very powerful capability that allows a computer to read signs, documents, books, like tags, and much more. And obviously, within the specific context, it can allow the identification of like wrongly labeled products, provide information about like expiration dates of like different products, and inform like quantity of a certain product in like a magazine or catalog. And it can also track packages during like development. And on a larger scale as well, the ability to read text from an image is honestly applicable to so many different ways that it's kind of crazy. It's up to you guys, obviously, to find even more uses for it. Autonomous assembly, it's pretty much what it sounds like. It's just robots making things in factories, and obviously computer vision is necessary for that, because you need cameras and input sensors to be able to make decisions in that factory, or for the robots to make decisions in a factory without human involvement or interference. And finally, defect inspection is basically when in the final stage of manufacturing, computer vision can allow systems to basically analyze the product and see if there's a problem with it before it goes out, prevents thousands, if not billions, of dollars of damage, and also can prevent like recalls. If you guys have seen that before, well, there'll be a problem in like a specific hardware component of like a perhaps a vehicle or something, and they'll have to recall all of those specific models of cars back to get that fixed. It's just a hassle, waste of money, waste of time, and computer vision is helping to solve for that. So pretty much what I'm trying to tell you guys is that computer vision is a hot topic right now in the world, and it will continue to be so going into the future, right? It's being implemented in almost every single profitable industry and will continue to develop in the coming decade, right? So in fact, Forbes is estimating that there's like $1 billion worth of startups in the field of computer vision coming up. And it just shows how important it is and how much potential computer vision has to truly change the way that the world works. And even furthermore, estimates show that the computer vision market will reach $41 billion by 2030, which basically means that companies around the globe will spend $41 billion annually in the field of computer vision. So it just goes to show if you guys are interested in computer science, you will see computer vision in the future, and it's going to be a really important facet of computer science as a whole. So it would be really, it would be worth your while to learn about computer vision and explore it further in the future. So that's pretty much what computer vision is doing right now in the world. And there's a couple of ways, specifically through tools and libraries, that we can access computer vision and you can really learn about it. The three most popular ones are on your screen right now. So Opencv, it's an open source machine learning and computer vision like software library. It's basically very common infrastructure, so you can use it on like any OS pretty much, and through like a number of languages like C++, Python, Java, MATLAB, and a couple more. And I think the biggest thing for OpenCV is in its name, right? It's open source, and you can access it through any OS for any language, which makes it very flexible, and you can use it at any time. TensorFlow is a very popular one as well. In fact, it's the most popular, I think, end-to-end open source machine learning platform. It has a comprehensive set of tools, resources, libraries, And again, like Opencv supports like Python, C, C++, Java, JavaScript, and it has actually a really interesting and cool like implementation, which is TensorFlow Lite, which basically allows on-device machine learning for like with edge devices. It What that basically means is that because of the reduced model size through TensorFlow Lite, you can download machine learning models onto certain devices, which means they can do the prediction without having to connect to the internet, which is amazing for like low latency situations. Like for example, while you were driving the Tesla, and the Tesla, or rather when the Tesla is driving itself, it needs to be able to make decisions on the fly really quickly. And models like TensorFlow Lite, which are really low in size but very high in accuracy, are perfect for such situations. Finally, the most popular, I think, free computer vision tool is Yolo, which stands for You Only Look Once. It was developed in 2016, so it's actually reasonably new and like it's in further development even in 2022. But it's also known as the fastest computer vision tool, even more than TensorFlow Lite, and it has a very low latency, which, as I just explained, is very attractive for people that are trying to develop models for very high stick situations. But like I said earlier, there's so many tools and libraries that you can use. So it's up to you to research and find the one that you like the most. But these are the most popular ones on the market right now. Apart from these tools and libraries, there's obviously companies that are investing, money and stuff like that in computer vision, right? So some of these biggest companies in the world, like Google, Amazon, and Microsoft, have been building and expanding on their computer vision platforms for years. Like they've spent billions of dollars on such technologies. And the reason this is important is because companies like Google, Amazon, and Microsoft, they have like an elaborate and well-tested algorithm that allows both individuals such as like me and you and also businesses to be able to access computer vision functionalities without needing too much machine learning knowledge, right? And I know I'll explain like the science behind how CV works a little bit later, but let me explain a little bit about what these companies do in relation to CV, right? So the way that computer vision works is that images need to be fed to a machine learning model so that it can learn what these images are depicting, right? So like if you want to make a model that understands that you're looking at an Audi Q7 instead of a general car, you would have to take hundreds, if not thousands, of pictures of the car and then use these images, feed it to the model to allow it to have a high accuracy and prediction rate. And the power of these companies is that they actually make the model and train it for you. So they, in doing so, they create extremely efficient and like accurate and robust, really, models that we can use. And these models are like 100 times better than what we can make because they have thousands of people working on it, like daily, and they test and train these models like every day. Microsoft alone has uploaded 6 billion images to their general object detection algorithm, and it allows it to recognize over like 10,000 unique objects. And the best part is that we can access all of these models and capabilities through APIs, so it's super simple. Um, I'm not sure if you guys have learned what an API is. You might have, but I'm just going to quickly go over it just in case. An API is an application programming interface. It's an easy way for two apps to talk to each other. Basically, if you wanted to make an app with the capability to, like, say, like I said earlier, read and extract text from images and videos, you can use these different APIs given by like such companies to bring these functionalities to your own app without having to code it yourself. Right? It's super easy. It makes your application robust and efficient. And that's pretty much it. For the so okay, I've hyperlinked Google and Amazon's computer vision platforms in the slides. So when you guys get them, you can like do a little bit of research if you want and look into it. I personally have explored Azure, which is Microsoft's like cloud, and through its custom vision platform. So that's what we're going to use for like the lecture slash the homework. I'll explain how it works a little bit later. There's like detailed instructions. But for now, just know that even though we're going to be using Azure, there's multiple companies that have had their own custom or computer vision platforms. Apart from these major companies, there's universities that are exploring, computer vision, right? And like it's namely like professors and student groups within, these prestigious universities that are doing their own projects and research papers and other stuff that's, related to computer science. And it's like contributing to the further exploration of the technology as a whole. And there's really two important effects that you guys should know, right? So first, when you guys start heading to university, you're going to have the opportunity to choose like these specialized fields, right? So whether that be AI, ML, or even computer vision, you can collaborate with professors and research, with other students even, and create applications that can really help people in like communities that need these technologies that you're going to end up exploring. And second, it signals a shift in the educational setting of what people are like learning, right? With growing like importance and investment in computer vision, colleges are allowing students to dive deep into the concept and try and understand what's really going on behind the scenes of these powerful algorithms that really have the potential to change and run the world. So I think that's pretty interesting. I have hyperlinked the computer vision like sites for like three different colleges that I thought were really interesting. But we can take a look at it in like MIT because I have it open here. And essentially they have like a number of like projects and different areas that they explore via computer vision, right? So like for example, robot overcomes uncertainty to retrieve buried objects. I think that's pretty cool. I mean, it's it's just really cool to see like all the different things that these college students, which are only who are only like a few years older than us, all the things that they're exploring through the use of computer vision. And UT Austin has their own projects as well, and um, the University of Michigan, for example, also has their own things. I think you guys can take your own time to do that, but it's just something that you should keep in mind because these colleges are signaling that they want students to be more interested in computer vision and stuff like that. That's quite like pretty much a quick genesis of what computer vision is doing in society today and like how it's being explored around the country and around the world really. And I think it's important to understand the context of computer vision so you guys can truly try and grasp the potential that it has. I know this is a little like different than the other concepts that you guys have learned, especially with like neural networks and all, because that's like all theory, complex procedures and all that. But computer vision is different in that it has the power, in that the power that it holds is best demonstrated through real world examples. Um, it's just a computer trying to mimic human vision, and I think it's easier for y'all to try to go from the top down to understand how it works, to understand like one layer of computer vision at a time. And I also know this is a little different than the other lectures because I know you guys immediately dove into like the nitty gritty of like the technology that you're learning pretty much immediately. But I thought it was necessary for you guys to understand how computer vision applies to the rest of the world because that's how I got into it. That's how I got excited about the prospect of CV and like how it can really help the world. But now that that's done, let's actually dive into the nitty gritty of how computer vision works and how computer science plays a role in it. So, you guys want to take a look at this like flowchart? It's called the computer vision pipeline. It basically shows the key steps that you take to go from like an input data, which will be a picture or a video, like video's individual frame, to the eventual output, which is like the image analysis or the model prediction. So right now it may seem a little complicated, but we're going to go step by step to explain each section. But before we do that, this is an example, like a specific example of like that very same classification pipeline. So, right, so I'll run through it just to give like a quick overview of each step. So right, so first an image will receive a visual input, which will be from like an imaging device like a camera or a sensor. And it will be either an image or a sequence of images, i.e. a video. But in this case, it's a picture of a motorcycle, right? So this picture of the motorcycle is sent through some pre-processing steps, whose purpose is to standardize the image. And common like steps for pre-processing include resizing the image, blurring, rotating, changing the shape, or transforming the image from one color to another, specifically from like a colored image to grayscale. And only by standardizing an image, which basically means making them the same size, can you compare them and like further analyze it in any way. And don't worry, I know it's a little weird. We'll get into the specific steps in a little bit as well. Next, which is feature extraction, you extract the features. It's basically like features help us define certain objects. They're information about the object's shape or color. For example, some features that distinguish like the shape of the motorcycle are the shape of the motorcycle's wheel, the headlights, the mud guards, and so on. Right. So the output of this process will be a features vector, which is like a list of the unique shapes that identify the object, right? And finally, this features vector is fed into a classification machine learning model, and basically it looks at the feature the vector from the previous step and it predicts the class of the image. So basically, you look through each feature, whether that be the wheels, the headlight, the exhaust, the fact that it has two wheels instead of four, and the model will like get closer and closer to finding out that this is a motorcycle. Um, that's kind of like a general description of the pipeline. So let's go step by step, right? The input image is literally just a photo or a video that's broken down, or a video that's broken down into frames. It's not really much to it. It's just a picture. The second step is where it gets a little fun, right? So pre-processing is crucial to standardize the image. So basically, all the images that are being compared have to be the same type, whether that be color, shape, or size, for you to compare them. The goal of this step is to make sure that your data is ready for the machine learning model, and it makes it easier to analyze and process like computationally as it is with images. The acquired data that you get, like basically the input data that I just talked about, is usually messy. It's coming from different sources. It's unorganized. To feed them to the model or the neural network that you eventually use, they have to be cleaned up, right? So more often than not, pre-processing is used to conduct steps that like reduce the complexity and increase the accuracy of the applied algorithm. So there's three common ways to pre-process an image, right? First is converting color images to grayscale. So I mentioned this a little earlier, but it's basically in that in many objects, color isn't necessary to recognize it. So grayscale can be good enough for recognizing certain objects, right? Because color images contain more information than black and white images. They add unnecessary complexity and they take up more space in the memory, right? It's primarily because colored images bring in the RGB values, which just makes it a heavier analysis, which makes it more inefficient. And you can see from the image on screen that this is a picture that's like in grace, half in grayscale, half in color, and you can see that the color doesn't really bring any important information for recognizing what's going on in the photo. You can do everything through like on a grayscale, and you can understand it just as well. The second way that a image is pre-processed, and this one is crucial for computer vision, because one important constraint, the second way is standardizing images. And this is really important because the constraint that exists in some machine learning algorithms, specifically the convolutional neural networks, is that the images need to be resized by unified dimensions. And since CNNs are pretty much the go-to for image analysis, when you're doing computer vision models, you have to standardize your images. So basically, that means that all the pictures have to have the same dimensions, right? And it basically scales each image to have identical widths and heights before being fed to the algorithm that you're going to be using. And finally, the last common way to like pre-process an image is through data augmentation. It's a little weird at first, but basically what it means is that you augment the existing data set with like different variations of existing images, right? So if you look at the butterfly on the screen, you can see like the original image is a very clear image of a butterfly, right? And on the right side, it'll show you like different ways that this image has been slightly changed. And the idea here is that you enlarge your data set and you expose the neural network to a wide variety of variations of your image so that it can recognize the objects more and it can recognize it in any shape or form, right? So you never want to train a model too specific, right? So in augmenting the data, you're allowing the model to look at a variety of the same object, thereby increasing its potential accuracy rate and allowing the model to recognize the object on a wider scale, if that makes sense. So after this, that's pretty much what like pre-processing the data is. Those are the three common. Obviously, there's more things that you can do, but it's like really specific. And most of the time, one of these three ways, or like a combination of them, will be more than enough for you to process your image. So after that comes the step of feature extraction. And I'm going to be honest, feature extraction is like the core component of the computer vision pipeline, right? In fact, the entire deep learning model works around the idea of extracting useful features which clearly define the objects in the image. So I think you guys may have learned about features in the neural network lecture, but I'm going to define them again quickly in the context of computer vision, right? So in CV, a feature is a measurable piece of data in your image, which is unique to the specific object, right? So it may be a distinct color in an image or a specific shape, such as a line, edge, or image segment. And a good feature is used to distinguish objects from one another, right? For example, if I give you a feature like a wheel and ask you to guess whether the object is a motorcycle or a dog, what would your guess be? It's gonna be the motorcycle. But if I gave you the same feature and asked you to guess whether the object is a bicycle or a motorcycle, the feature is not strong enough to distinguish between both objects. So then you need to look for more features like a mirror, the license plate, the pedals to essentially find what collectively describes a specific object. So in this image, you see a picture of a motorcycle, right? We're going to continue this analogy. And basically, you're going to feed the raw input image, or yeah, the raw input image of a motorcycle to a feature extraction algorithm, right? Now, let's treat this feature extraction algorithm as a black box. It's not really important how that works right now. It's really complicated, kind of unnecessary. Let's just pretend like it's able to successfully extract a couple of these features, right? And eventually, after extracting these features, it's going to be these features are placed in what's called a vector or a feature vector. And it's a 1D array that has a robust representation of the object at hand, right? And this is really important because a machine learning model is only as good as the features that you provide it, because it's the foundation upon which like the pattern analysis is made for the computer to recognize what it's looking at. So what is a good like feature? Like what are the key components or the key characteristics of a good feature, right? So one, it has to be identifiable. Like, I mean, that's pretty obvious. You have to be able to look at the image and identify the feature pretty clearly. The second key thing is repeatability. This basically means that this feature is consistent against all types of like the object that you're like scanning. Uh, it's a little complicated, but like for example, this motorcycle has a wheel, right? But like if you're looking at a specific like brand of motorcycle, like a Kowalski, like if it has a specific characteristic, you don't want that to be a feature. You want a feature for like some to be something that every motorcycle has. So that would be the wheels, the headlights, the seat, the exhaust pipes, the mirrors. They're all unique to a motorcycle, right? Because it's different than what would be on a car. But between different types of motorcycles, they might have like differences, but you don't want those differences to be features, if that makes sense. The third thing is you want these features to be easily tracked and compared. It shouldn't be like some really small or like basically it should be something that you can really see within the picture. And it has to be fourth, consistent across different scales, lighting conditions, and viewing modes, right? So if you can only see the feature at a specific angle from a specific like distance, then it's not a good feature, right? It has to allow a model to look at any type of photo of the object and recognize, hey, that this is a motorcycle, right? And it should still be visible in like noisy images or only when part of the object is available or visible. Noisy image is basically like there's a lot more going on in the picture. So like right here, this is a motorcycle, right? But like there's not really much else. Usually a motorcycle will be somewhere with like other cars, other motorcycles, people. So you want to choose something as a feature that you can still see and you can still notice when there's other stuff going on in the picture. Yeah, that's kind of like pretty much it. Once you have your features vector, you can use these features and feed them to a machine learning model that is being used, and then the model can like learn to predict the object that you're training for. In the same example of the motorcycle, after like thousands of features are made, your model can use them to train itself comprehensively, allowing it to identify a motorcycle from a completely new image. Like that's the entire idea. So you want to train the model so that it can look at a completely new image that it's never seen before and be able to recognize what's going on in the image. So let's take a moment to talk about the deep learning machine learning model that is most commonly used for image analytics. I mentioned it earlier. It's the convolutional neural network, also called a CNN, right? And I'm sure you guys might have heard of it, but I'm going to explain it on a surface level so you guys can like get an idea of what these models really do. I'm not going to go into the like really detailed analysis of what they do because honestly, even I don't understand it very well to that level where there's multiple layers, a pooling layer and stuff like that. I don't think it's necessary either because all of this stuff is available to you like through like the different companies that I talked to you about earlier. So this is more for your understanding so you know what's going on. Not everything should be a black box. you want to know what's going on behind the scenes, right? So basically, a CNN works by breaking an image down into smaller groups of pixels called a filter. Each filter is a matrix of pixels, and the network does a series of calculations on like these pixels, comparing them to like pixels in a specific pattern that the network is looking for. In the first layer of a CNN, it's able to detect high level patterns like rough edges and curves. But as it performs more and more convolutions or like layers, it can begin to identify specific objects like faces and animals. But how does a CNN know what to look for and if its prediction is accurate? This is done through a like large amount of like label training data, which is basically your features vectors, right? This is like the training data that allows the CNN to be as powerful as it can be. So when the CNN starts, all of the filter values are randomized, and as a result, initial predictions that it makes make pretty much no sense, right? But each time a CNN makes a prediction against labeled data, it uses an error function to compare how close its prediction was to the image's actual label. And based on this error loss function, the CNN updates its like filter and starts the process again. And ideally, each iteration that it takes, it performs with more accuracy until it eventually reaches the desired like accuracy level that you're aiming for, right? And it uses this error loss function again and again and again until it can successfully identify the object that you're looking for. And CNNs are like great. They work brilliantly with static images, but they fall short in videos, right? And video analysis is just as important as image analysis in my eyes. And though a video is like made up of multiple image frames, all of a sudden, like the need for context is very important, right? So, for example, an individual frame in a video may show a half-filled box, but without knowing what happens before or after this frame, how can we or the model decide if this box is being packed or unpacked? There's literally no way. So the context is crucial for such analysis, but CNNs basically they show up lacking, right? They see convolutional neural networks can show spatial features and they can show visual data in an image. But what they can't handle is temporal or like time features, which basically explains how one frame relates to the one before it, right? And the way to solve this is to take the output of the CNN for an individual frame and feed that to a temporally sensitive model, a recurrent neural network or an RNN, right? While a CNN treats a group of pixels independently, an RNN can retain information about what it's already processed and use that in its decision making. So RNNs can handle many types of inputs and output data. In the example of like classifying videos, we can train the RNN by passing it through a sequence of frame descriptions, right? So whether that be empty box, open box, closing box, and finally a label packing, the RNN can process each sequence, and again, it'll use a error or loss function, like just like the CNN, to compare its predicted output with the correct label. Then it adjusts the weights and processes the entire sequence again until it reaches a higher accuracy. It's a little complicated. I know that. And honestly, if you don't understand that, it's totally fine. But the important thing to know is that CNNs are good for static images, right? You take a picture and instantly, like within that instance, it'll tell you what's going on. But the second that you introduce context and like connected images, which is basically a video, CNN becomes kind of useless, right? Because it'll tell you what's happening in the picture, but it can't tell you what's happening in the picture in relation to everything else. And this is really important because RNNs are crucial for things such as self-driving, right? Because when, again, we'll take this example again, when a Tesla is driving itself, right, it cannot stop and take a picture and wait for a CNN to give it input, right? Or give it an output. It uses these recurrent neural networks to have a live feed of or a live stream of analysis going on the things around it, right? That's how it's able to drive by itself, right? It's able to see red lights, stop signs, cars around it, people around it, and other like road signs to be able to adjust itself and successfully navigate its environment, right? Without an RNN, it would never be able to do so. And I think that's the important thing you need to know. Like RNNs are for temporally sensitive frames, and CNNs are for like static images. But that's the entire computer vision pipeline. um, yeah, to like summarize, there's four main parts, right? There's the input image taken by a camera or a video, again, taken by a camera or stuff input from sensors. There's image pre-processing. We talked about the different types, whether that be color to grayscale, standardizing, or data augmentation. There's feature extraction, which the biggest thing is that it takes features of the image that it's analyzing, and it makes 1D arrays called feature vectors that contain all the unique information about that object. And fourth and finally, there's these deep learning models, which are the CNNs and the RNNs, that use the features vectors to be able to train itself, and eventually they can predict what object or what's going on in a picture, right? And that's kind of how the pipeline like works and connects. Again, it's a little high level. There's like always stuff you can dive deeper into, like CNNs and RNNs, but that's kind of all you need to know on what happens. And like I said earlier, all of this model making and training is done by bigger companies, right? So next we're gonna like explore like Azure's custom vision platform, and it'll show you like the power of these big companies, right? And initially, I'm not gonna lie to you guys, your project was to make your own CNN using TensorFlow and Keras, but I feel like this is a little more relevant and hands-on, and it is pretty much it's genuinely exciting, right? And I'll tell you what happens, but it's basically how I first learned about classification models and all that. So I want to walk you all through, what's going on in with computer vision and these like what these tools can really do for you, right? So, okay, let's go off the slideshow. You're gonna want to go to, you're gonna want to go to Custom Vision, which is basically Microsoft's platform, right? You're gonna go to customvision.ai, and you're probably gonna be taken to, you're gonna be like taken to a pop-up that looks like this because you probably don't have an Azure account. If you do, it will open up automatically, but I'm gonna bet that most of you guys don't. So you're gonna have to make an Azure subscription, right? So you want to click sign up for Azure. It's gonna give you this. It's gonna open up a new link that allows you to make your own account. And if you don't have an account, sorry, if you don't have your own like credit card or anything, you're gonna have to ask your parents for it, for their information, and you have to input that. And the reason that this is so is because for some services, Azure obviously requires you to pay for them. Um, they have very powerful tools that even like large scale businesses use. But for the activities that we're going to be doing, it's all free, or it will all be free, right? You can always do a paid version of it, but for what we need to do, it's all free. But you have to enter your credit card information for you to get an account. If you have a problem with that, I'm not really sure. Contact me in the Discord, or yeah, contact me in the Discord. But just tell your parents that it's free if they have a problem with it. I can talk to them if you guys want. But I think it's really important that you guys get some hands-on experience with what like the industry offers, right? So after you make your account, you sign up like with the terms and conditions and all that. You go back to the original link that I told you guys about, and you just refresh, and it should take you to this page right here. Um, and this is basically Azure's custom vision platform. I've used this for the last 3-4 years, no, four plus years, for my own projects and stuff. So basically, what you want to do, you want to click new project, right? Obviously, you want to enter a project name. So let's just say learning computer vision, right? A description, let's just say AC side 2022. Now a resource, you're not gonna have any if you just made your account. You can just create your own, and basically you will want to name the resource whatever you want. Probably something relevant. Subscription, choose the only one available. It's the free one. Resource group, you probably won't have one. You're gonna there'll be like a pop-up here to like create new. You create your own resource group. A resource group is basically just like a folder in your file system. It just has all your resources that are related to one another in one section. So you want to choose your resource group, the kind you want to change to custom vision prediction. Location to South Central US. Obviously, if you're in the South Central US, I think everyone that signed up for AYSI this year was local to Texas. But if you're not, there's a ton of locations. Just choose the one that's most applicable to you. And the pricing tier will be a 0 or F0, and you want to change to F0. I think it's the free one. If you don't have this option, just choose F0. I think it's also free, but there's like a little difference in like it's background stuff. You don't have to worry about it. It's all free. If you haven't paid for it, it's all free. You create your resource. Your project type, you want to choose classification. The difference between the two is that classification allows you to identify objects in an image. Object detection tells you location of objects within the image. So obviously, if you want a project in object detection, you can do that later. But for our means, you want to do classification. And the classification types, you want to do multi-class instead of multi-label, because for your first time, you want to do one tag per image. And what this basically means is that in each image that you're going to train the model with, there's like one thing that you like one object in the image, right? So like I'm gonna eventually like show you guys an example of like just uploading a picture of a lab. So there's only one Labrador in the picture, and there's only one tag for the image. But like for example, if there was a lab and a German Shepherd, then you could do multiple labels in the same picture. So it has a lot of flexibility and versatility for you to do whatever you want to do. Domain, you want to choose General A2. Don't worry about this right now. This is for making more like small models so you can export them to on device. Just don't worry about this right now. It's just do General A2. And then you want to do create project. It will load and will open up this type of basically UI. So quick overview, training images. This is where you add images to train your model. So for example, let's say if I want to do this, I downloaded a picture earlier of this lab. I'm going to upload it. It'll take a second, hopefully. Yeah, okay. So this is what it will show. You want to upload the file. They'll say uploaded successfully. You open it, right? And you want to add, Labrador Retriever. You can name the tag whatever you want. If you wanted to be more specific and you were doing it for all labs, you could be like, white Labrador Retriever. It's up to you on what you want your model to be able to detect. But you want to save and close. And all of a sudden this picture will disappear because you're in the untagged section. You're going to click tagged, it'll be here, right? And obviously this is just one picture, and inevitably you're going to have to create, or rather upload a lot more pictures, and as well as have multiple tags, right? So you're going to have white Labrador Retrievers, maybe you want to add a black Labrador Retriever, yellow one, so all the different colors for the breed, and eventually you'll be able to make a model that can successfully predict things, right? And then eventually when you have multiple tags, you can like search for tags here, and you can see all the tags that you've used, right? Leave this as workspace, don't worry about it. You can always add images, and so this is the performance section and the prediction section. I was not going to make a new model just for predicting Labrador Retrievers, so I'm just going to show you guys this. This is my like a project that I've done for science fair and stuff like that. I used Azure as I told you guys. So this is my so okay, I'll show you guys around. So basically my model was for like recognizing common things in my house. So like it's pictures of like stuff around here. You can see all the tags that I have. It tells you amount of pictures I've uploaded for each one as well. Untagged, there'll be nothing. I've tagged everything. But the main thing that you can do is like once you press train, you do advanced training, and you train for an hour, and you can train up to 96 hours. But for you guys in models, especially early, you don't need anything more than an hour. You can always do a quick training as well, but advanced training is more thorough. And eventually it'll give you these 3 metrics, as well as like a more detailed analysis on these metrics per each tag. Precision is basically like your accurate. It's like based on the predictions that your model makes, how many of them are like correct, right? It's like basically an accuracy rate. A recall rate is like out of all like the possible true positives, how many did your model identify? Which basically means that if it's given X amounts of pictures that have like a car in it, like a Tesla in it, then how many of those did the model identify as a Tesla, right? So it's not like exactly the accuracy rate, but it's more specific. And the AP score is just like it's just a general statistic that you want to be as maximized as possible. It's basically like a metric that combines the precision, recall, overall accuracy, and stuff like that. And it's basically Azure's own thing, as far as I know. Um, and you want these like numbers to be at least above 85% when you're making a model, but like obviously the higher the better. And it'll tell you per tag, right? What is your precision? What is your recall? What is your IP? And it'll tell you if your images and if they're too little. Like for example, for my master bathtub, like the images are only I only took 32 pictures of it. It's red because that's not enough for the model to understand what's going on and be able to recognize it at all times. So you can like there's a lot of like powerful things that you can do with Azure's custom vision, and you can also do predictions, which is basically like you can do a quick test, upload your own a picture of like something that relates to your model, and see if it's able to recognize it. Right. I don't have any pictures of my house downloaded, but pretty much you guys can do that. And yeah, I think that's pretty much it. It's actually quite easy to navigate around, and I think you guys should have a little fun with it. Uh, One of the biggest things that I want you guys to be able to do, by the end of like AYSI's like Sci course, is that you are comfortable with these custom vision platforms and how they work, and um, like I want you to be able to make your own models because these are tools that are industry level and like they really give you the chance to make your own things instead of having to worry about like CNN and stuff like that. Like you see how all of this stuff that I just did doesn't require any knowledge of like machine learning, like real machine learning. Like you kind of have to train a model and you kind of have to train it or you have to test it. But like you don't really need any machine like there's nothing about CNNs, RNNs, nothing about the computer vision pipeline that you need to know because it's all done for you. And that's the beauty of these like big companies making these algorithms for you because all that stuff is done on their end. You're paying for it to be able to access these through this platform, through different APIs. And I think that's really special. So yeah, basically you guys' homework is to basically make your own models. I want everyone to make a model that can have an accuracy rate, or rather have a precision recall and AP score of above 85%. Um, if you guys want ideas for like what to train on, you can train like pictures of your car, for example. I think that's one really easy way to do. Because basically the type of pictures that you want to take of an object have to be from different distances under different lighting conditions, from different angles. Because, like I told you earlier, it allows these models to make better features, which then allows these models to recognize them in pictures more successfully, if that makes sense, right? So choosing something like your car, you pull into your driveway or you're in the alley, just do 360 photos. You upload like 250 photos to the custom vision AI platform, and you train it, you test it, you get your scores within an hour. And I think that if your scores aren't high enough, you need more pictures, you can choose another object, stuff like that. But choose a household item that you can find, whether that be your car, whether that be a sofa, a bed, something like that. Take a bunch of pictures of it, use custom vision, Azure's custom vision platform to make your own machine learning model. And I want you guys to send a screenshot of your scores and your tags in the Discord. I'm not sure when the submission date is. I'll let you guys know in the Discord when Rago gives you the link. But that's pretty much all I have for computer vision. It's not that long of a lecture. It's like I think it's ended up being less than an hour eventually. but I think it's really cool. Computer vision is definitely something that I personally am really interested in. I've worked with it for like 4 to 5 years now. For my own projects, I think it has the potential to really, change the world, one step at a time. And we're seeing it how it's like shifting that way, through these companies, through universities, through schools. I think it's really cool. But yeah, that's pretty much it from me. I don't think I have anything else to tell you guys. If you guys have any questions, please feel free to ask me in the Discord, personally in the channel. Um, you can ask for my phone number if you guys want to text me if you're more comfortable that way. Uh, I think it's really important to ask questions about computer vision, especially in the beginning, because I know the first time I learned it, I was super confused. So, ask questions, ask each other questions to make sure everyone else understands. Send in your screenshots, and I'm really interested to see what you guys choose as your household objects to make your models on. Um, and if you guys want more work on it, let me know. I'll put some more assignments in the chat that you guys can further explore Azure and stuff like that. But yeah, that's pretty much it. That'll be all for today's lecture. Um, it's a short watch. I'm pretty sure it'll be uploaded a little later in the day. I'm not sure completely. That's not entirely up to me. But I'm sorry I couldn't do the session live. By the time you guys are watching this, I'll be at work. Um, I have an internship and stuff like that, so I can't um, teach live. But I really wanted to teach about computer vision, as I mentioned earlier. It's one of my passions and all that. So yeah, that's pretty much it. I hope you guys have a good rest of your day. Again, homework assignments, we got them. Yeah, that's pretty much it. Thank you so much for watching. Have fun with your research and endeavors and all that. And let me know if you guys need any help. Office hours. I think the form is already out. If not, it'll be out later. You can always text me or Raga for help with AYSI stuff, and you can text me for computer vision help. Yep, that'll be all. My name is Adil Hussein, and thank you for watching today's lecture. All right, bye.